And today, of course, is Halloween. So, anyway, that has no bearing on the electrons, which is a good thing. When we talk about electron configurations, we're talking about how the electrons in any individual atom are arranged, okay, how they're configured. And everything about how that atom behaves is based on its electron configuration. These are pretty important. So in this chapter, we've started to talk about sort of where the electrons live, metaphorically speaking, of course. And we're going to look at the rules for placing electrons. Then you're going to learn 3 different ways to represent electron configuration, going from the biggest pain in the tuchus one to a less pain in the tuchus one to a super shortcut. Okay? And that super shortcut will follow you into the next couple of chapters, and you'll be able to use that super shortcut to look at a periodic table and immediately go, oh, that has a blah, 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 blah arrangement. And it's pretty slick once you get it. But you kind of have to, it's like learning to ride a bike. You have to learn the hard way. You got to drive into the ditch a few times. So we're going to learn the long way first. Okay, there are 3 rules that govern electron configurations. Okay, so we're going to go through each one of them. And the first one is called the Aufbau principle. What the Aufbau principle says is that electrons are lazy. Electrons go into the lowest energy orbital possible. So they're going to fill all the low energy orbitals before they start filling higher energy orbitals. Guess which main energy level has the lowest energy? We've talked about this. 1. Next energy level is 2. Next one is 3. But even within those energy levels, the orbitals have different amounts of energy. So as you go up an orbital, or knock orbitals off the table, as you go up in orbitals, they have higher energy levels. Okay. There's a chart that you're going to create for the first time today, and you will write this chart out repeatedly on your. You'll take a little quiz for me probably Thursday, and you'll get 2 points just for writing this chart. You'll get some points for writing this chart on the test for this unit. And the chart looks like this. And I'm going to show you how to write this easily. So I'm going to delete this slide. Start off by writing 1s. That's your lowest energy level, lowest energy orbital. Okay, this is easy, Moser. Then we go to 2s, and next comes 2p. Second main energy level, 2s is the lowest energy, 2p is the next highest in energy. Then we write the 3s, 3p, 3d. So we're building this sort of weird triangle. 4s, 4p, 4d. And notice that I'm being really careful to line these up neatly. That does matter, believe it or not. And then we write in 4f. Below that I'm going to put 5s, 5p, 5d, 5f. We know that 5g orbitals exist. We're not going to write them. We're not going to write them. We're not going to go out any further than 5f, and you'll see why in a second. So then we're going to write 6s, 6p, 6d, 6f. You'll see a lot of representations don't even write the 6f, and again, you'll see why momentarily. 7s, 7p, 7d. We can probably actually stop at 7d. Is there a 5g? Yeah. Is there a 6g? Yeah. Is there a 7g? Yeah. You're going to see why we don't have to write them. So I'm going to actually switch colors. And you need, okay, how many of you think you can draw a straight line? That's all you need to be able to do. No? It doesn't have to be perfectly straight. The reason you have to be able to draw a straight line is because you're going to draw arrows through these orbital levels. There's your first arrow. Goes through 1s. 1s is the first energy level and the first orbital that fills. Then comes 2s. No surprises so far. We go 1s, 2s. Then we go 2p. Then we go 3s. Okay. I don't see what's so complicated here. So after 2p, the next energy level, we hop up to the third energy level. We put electrons in the s orbital. Then we go to 3p, and then guess what happens? Something really weird. From 3p, the next energy level and orbital that we fill is 4s. 4s is actually lower energy than 3d. So this is what we talk about when we say there are overlaps. So then we fill 3d, then 4p, then 5s. So we've now started filling in the 5s before the 4d. 4d to 5p to 6s, 4f to 5d to 6p to 7f. And this is where you can see 5g would come in. You're not going to get to 5g. And a lot of times you'll see this chart replicated looking like this because you're unlikely to even fill something that goes up to the 7p. And you'll see why as we start to do actual examples of these. Being able to draw this chart is critical because you can't do electron configurations above 3s without it. So basically starting now for the next couple chapters, every time you sit down to take a quiz or a test or do homework, you're going to draw this chart on your paper. I do this chart on my papers as I'm doing these things. I've tried, I've gotten cocky and thought, I don't need to draw the chart. I know my overlaps. No, I don't. If I don't draw the chart, I screw it up. So just get used to drawing the chart. You'll get really good at it. That's the first rule, is that they go into the lowest energy level first. So the metaphor that I have for you on this, and I'm going to shrink our little chart, the metaphor that I have for you is what I call the dorm metaphor. Most of you are going to be heading off to college in the years to come. And when you move into a dorm building, probably a high-rise, possibly without an elevator, and you're carrying everything that you're going to use for the next year on your back, you've got backpacks and suitcases and maybe a dorm refrigerator strapped to your head, I don't know. You really don't want to climb any more stairs than you possibly have to. So if there is a room available on the first floor, you're going to take it. Because you don't want to climb any more stairs than you have to. Electrons are lazy. They're not going to go up any higher in energy than the lowest energy spot available. If the first floor is full, you'll go to the second floor. You're not going to climb to the third floor if there's space available on the second floor. Okay? It's a pretty simple metaphor, but it works. And you'll notice that I've got a crooked floor up there. The overlaps are difficult to represent with this metaphor. That's where the metaphor breaks down. Oops, I wasn't recording. Okay, Wolfgang Pauli, Pauli exclusion principle. Anyway, sidebar about Wolfgang Pauli. He ended up doing a whole series of letters and interviews with Carl Jung on physics and the nature of consciousness late in life. What the Pauli exclusion principle says is that no two electrons in the same atom can have the same address. We said that there are those sets of quantum numbers. There are four. There's principal and angular and magnetic and spin. Each one of those gives a piece of the address. And if we go back to the dorm room metaphor, it's kind of like saying, you know, there's the building, there's the floor, there's the room number. But if you still have two roommates in the room, you have to differentiate between like desk A and desk B in terms of where mail's going to go. So So you have to be able to differentiate between the two electrons that are in any orbital, and we do that with spin. We represent spin with single-headed arrows. So if we imagine in the 1s orbital, and I'm representing the 1s orbital by writing 1s and then putting a little line, and there are how many electrons in any given orbital? 2. We call one spin up, one spin down. We write those little single-headed arrows. You can write them as double-headed arrows, though it's typically shown as a single. I think your book may show double heads, but... Okay, so we've got rule 1. Electrons are lazy. They go to the lowest energy orbital available. Rule 2, we have to differentiate them. They can't have the same address. They can't have the same set of 4 quantum numbers. So we differentiate them as spin up and spin down. This is the one that's trickiest. This is Huns' rule, and I don't care that you know which one is Huns, which one is Pauli's, and which one is Aufbau. I care that you're able to use them. I think that's more important. Orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second. Huh? If we go back to the dorm room metaphor, and I'm going to focus on the second floor of the dorm. So on the first floor, there's a terrible little dorm bed. If you get to the first floor, and there are people there, you're going to keep moving. You'll climb the stairs, you'll go to the second floor, you'll go to a higher energy level. So if an electron is in an atom where the 1s orbital is full with 2 electrons, it has to occupy the second main energy level. And if that electron gets to the second main energy level, and it gets to the 2s orbital, and there's 1 electron there already, it'll occupy 2s. Is having a roommate ideal? Maybe not. But having a roommate is less hassle than climbing to the next energy level. And remember that the 2 p's are slightly higher energy than the 2 s's. So right now we're using all these metaphors about, you and a roommate and climbing stairs. If we think about this in terms of actual electron and subatomic particle behavior, are 2 electrons attracted to one another or repelled? They're repelled. 2 electrons don't really want to be in the same space because they both have negative charges. Like charges repel. So to occupy an orbital together, those 2 electrons have to overcome the force of repulsion. That takes energy. It takes energy to overcome a force of repulsion. But it takes less energy to do that than it does to climb the stairs. It takes less energy to overcome the force of repulsion than it does to go up to the next energy level. Well, what if you get to the dorm and the 1s, the first floor room, is completely occupied. The second floor room, the lowest energy level, where I'm showing sort of a half level here on the second floor. What if the second floor, the lowest energy room, has also got 2 occupants? Well, then it's time to keep hiking. And it just so happens, let's see, copy, that there are 3 of these next rooms. So the 2 p's, the 2p orbitals, all have the same amount of energy. These beds are getting pretty tiny. Copy, paste, paste. So we've got, these are the 2 p's. 2px, 2py, 2pz. Because remember, we have p orbitals oriented along the x, the y, the z. So if you get up to that 2p level, and you walk into the first room, And sure enough, there's somebody there. There, we'll have them sitting on the bed. The force of overcoming the repulsion, the amount of effort it would take to overcome the repulsion of having a roommate is less than the amount of energy that you would expend to just go to the next orbital, go to the next room. So what you'll find is that you'll have one electron in every orbital until there are no more options left at the same energy level. If they have to go up a level, they will not share an orbital. So you're going to get one electron in each of those until there's no choice. Now, when we get to this point, and the options are share an orbital or go up an energy level, they will start to share orbitals. But until the point at which there are no more options available on the same energy level, they're going to occupy one at a time. So now you'll start to see them fill in. At this point, we could still fit one more electron on the 2p subshell before anybody starts going to 3. Okay, that's the 3 rules. Now we're going to actually do the practical work of representing these configurations. So you'll need your periodic table. And we're going to start off with, carbon. What the heck? We're carbon-based life forms. Why not? So, does everybody have carbon located? How many electrons does carbon have? How do you figure this out? So carbon is starting off with, how many electrons hold up fingers? Carbon starts off with 6 electrons. So the first kind of notation that we're going to learn is called electron configuration, or I'm sorry, this is called orbital notation. Okay. There are 3 forms of notation we're going to learn. This is the first one, orbital notation. It's called orbital notation because you show every stinking orbital and it's a giant pain in the butt. It's okay, you don't have to do it for long. You have to master it so that you can move on to the shortcut. So, what's our first orbital? 1s. And that's how we show an orbital in orbital notation. We name it and we put a blank line over it. That's an empty orbital. What's our next orbital? 2s. What are our next 3 orbitals? We got 2px, 2py, and 2pz. That'll be plenty to deal with carbon. All right, so I'm going to change colors to show our electrons. Where does our first electron go? What's the lowest energy orbital? 1. Where does our second electron go? 1s. It's the lowest energy orbital. That electron will take a roommate rather than climb the stairs. Where does our next electron go? 2s. How many electrons do we have? 6. Okay, so we're down 3. Where's our next electron go? 2s. Because 2s is lower energy than 2p. So we're now up to 4 electrons. This is all on the first main energy level. This is all on the second main energy level. So they've had to start climbing the stairs, but 2s is lower energy than 2p. Where does our next electron go? 2px. Whoop. Okay, this is where it gets not really tricky. So we now have 5 electrons placed. We have 1 more to go. Where does that last electron go? 2py. It's not going to take a roommate. The 2p's are all the same energy level. It doesn't take any more energy to go into one of those other 2p's than it would take less energy to go into the other 2p than it would to overcome the repulsion. Okay. That's the orbital notation for carbon. That's it. It's not hard. Let's do a couple more that don't have crossovers, and then we'll start working on crossovers. 9. So it's got 9 electrons. I'm going to represent my orbitals: 1s, 2s, 2px, 2py, 2pz, and that'll do. And I'm going to go ahead and make this little notation for myself, that I've got the first man energy level, the second man energy level. All right, where do my first 2 electrons go? 1s. I like making that noise when I make the electron arrows. You can too, I'll understand. Okay, 2 down, 7 to go. Where do my next 2 electrons go? 2s. Gesundheit. Okay, 4 down, Gesundheit. 5 to go. Where does my next electron go? 2px. Where does my next electron go? 2py. Where does my next electron go? 2pz. Okay, I've got 7 down, 2 to go. Where does my next one go? Back to 2px, back to 2py. That's the electron configuration for fluorine. So you've got one little lonely orbital that only has 1, but everything else is doubly occupied, fully occupied. As I said, it's a good habit to get used to just putting that down right away. So let's go ahead and we'll do 2 more before we get to anything with a crossover. Let's do sodium, shall we? So how many electrons does sodium have? So we're looking at 11 electrons. I'm going to go ahead and write my orbitals in. So I've got the 1s on the first man energy level, the 2s and 2p's on the second man energy level. I have 3s shown, which would be on the third man energy level. We're not going to go any higher than 3s. Where do my first 2 electrons go? 1s. 9 to go. 2s. Now, here's the thing. Don't get sloppy. Well, I know I'm going to fill in the whole 2p, so I'm just going to do them doubly. Don't do it. Do that, then do that. Don't build a bad habit. Okay? So now I'm up to what? 2, 4, 6, 8, 10. I got 1 to go. Where's it going? 3s. That's the orbital notation for sodium. How many electrons does phosphorus have? 15. 15 electrons. So I'm going to write them down, 1s. So I've got everything written up to the 3p subshell. There's my first man energy level. There's my second man energy level. There's my third man energy level. Okay. Go ahead and do this on your own. Look up when you're done. You have something that looks like that. We are now going to go big or go home. What the heck? Let's go for one of the magnetic triad. Let's go for iron. So this is Fe. How many electrons does iron have? We got 26 electrons. So we're going to draw in our orbitals, but we need to be careful. Why do we need to be careful after we get to 3p? What fills after 3p? 4s. It doesn't go from 3p to 3d. It goes 3p, 4s, and 3d. And I'm obviously going to have to shrink this a little bit. For the p orbitals, we have, the neat px, py, pz. For the d orbitals, we just call them 1, 2, 3, 4, 5. They have orientational names, but they are way too weird for what we're doing. So we just reference 3D1, 3D2, 3D3, 3D4, 3D5. And there are 5 d orbitals. Okay, let's start filling. You go ahead and fill, and I will fill and look up when you're ready. Counting by twos makes this nice and easy. You'll notice I tend to go 2, 4, 6, 8, 10, 12, 14, etc. Up until you get close. Do you have something that looks like this? I'm going to go ahead, and there's my 3rd main energy level. And then my 4th main energy level starts there, but it would be continued up there if I had a larger atom. Okay, questions on this form of notation? I'm going to let you practice this. I'm going to give you some homework from the book and let you work on it. Once you've practiced this for a little while, I'm going to show you the first shortcut. It's not a big shortcut, but it's a shortcut. And then probably Thursday in the second period that we're together, we'll learn the really serious shortcut. Okay, let me get the homework up. Okay, so for a couple areas that are typically confusing for people, do you understand why 4s fills before 3d? Okay, so we're cool with that. I had a number of people say, like, I don't get how these are alone. I don't understand that. So let's look at, let's look at the next element up. Nickel is Ni, one more of the magnetic triad. How many electrons does nickel have? 28. So I'm going to go ahead and write out all the orbitals up to the 3d subshell. Be really careful after 3p, because what fills after 3p? 4s. Then the 3ds. Okay, so they're all visible. I'm going to mark my main energy levels just because it's useful, I think. First main energy level, second main energy level, third main energy level, and then my 4th main energy level, which would go on up to here if I had more electrons. Okay. So I'm going to start filling. 1, 2, because I know that they will share if the other option is going up in energy level. So I'm going to put 1 in each of my 3 P's before I put 2 in any of them. 1, 2, 3. 1, 2. I'm sorry, 2 P's. 1, 2, 3. 1, 2, 3. Where do they go next? 4s. 1, 2. Now, those 3 D's are all equal energy. So before any 2 electrons are going to share an orbital and overcome their repulsion, they're going to spread out 1 per room. 1, 2, 3, 4, 5. What am I up to here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25. So I got 3 more to place. Now at this point, they have an option. Either you start sharing the 3d orbitals, or you go up an energy level to the 4p subshell. It'd be more work to go up to 4p, so they're going to start sharing. 1, 2, 3. I have 2 lucky electrons on the end that don't end up with roommates. If we added more electrons, they would. Okay. I'm going to tell you that on the chapter review, 11, 13, basically 11 through 17 odds, 18 through 20 A and B only. 23 is the one where you're practicing writing orbital notation. I would like you to do some practice writing orbital notation before you leave here today. We're probably going to go ahead and we'll do the next step tomorrow. I think I'll give you the rest of the time to work on this, and I'll work with a few of you who need some extra help. And then tomorrow we'll introduce the shortcut. So I want you to make sure that you have done 23 before you leave here today, okay? That's it.